Dear students, in the last class, we have seen how to analyze the algorithm and which are the methods. Okay, so as you already know, like there will be space complexity and time complexity, and there will be three type of methods to analyze. Now, today we will see growth rate or rate of growth. This is another concept which is used to analyze the algorithm. The greater the amount of data, larger the amount of resources required by an algorithm. Therefore, the resource growth rate is a piece of code in the form of function fn. Okay. Commonly used rates of growth to analyze the algorithm are: first one, constant function. Okay, commonly used growth rate analyzation concepts are constant function. A constant resource need is one where the resource need does not grow. That means anytime if you are taking, the resource will not grow. It will be a same position or maybe the same resources required. Okay, that is the concept of constant function. There will be a constant resource for that operation. And the best is like as I said in the last class, the assignment operations, addition, subtraction. Okay, these type of operation we'll call it as a constant function. The simplest function with some fixed constant. Okay, for example, assignment of variable, like here we have seen c, such as c is equal to 10. We took one constant c and we have assigned one value to c equal to 10 or c equal to 2, etc. The constant function is calculated as fn is equal to c. Okay, fn is equal to c. That is, for any number n, the constant function fn assign the value c. The constant function is used to add two numbers, initializing value to a variable, comparing two numbers. The graph of such growth rate is represented by horizontal line, you can see. So as the value increases, the resources will be same. There will not be any differences. That means always for the n values, the growth rate will be same. Okay, that it indicates constant function. Second one, logarithmic function. Logarithmic growth rate is a growth rate where resource need increases by 1 unit each time. Remember, logarithmic growth rate is a growth rate where resource need increases by 1 unit each time. That means the data is doubled. Maybe for example, if I am taking I is equal to I plus 1 or I equal to I plus 2, then it may be a logarithmic function. It is calculated as fn is equal to log n, and we will take one base. That means the base must be greater than 1. It must be a constant greater than 1. This function is defined as x equal to log n to the base b. If and only if bx is equal to n. As we know, x equal to log n and b is base. And the base into this x value must be equal to n, where value b is called base of the algorithm. And here you can see the graph, how it looks. So it is go on increasing in upward direction as the value increases. Next is linear function. Another simple important function is linear function. Okay, and it is calculated as fn is equal to n. given an input value n. The linear function f assigns the value n itself. A linear growth rate is a growth rate where the resource needs an amount of data directly proportional to each other. Okay, that's why you can see in the graph. So both are changing, directly proportional. Resource need as well as the value. If the value increases, even the resource increases. Okay, resource need is increases. The growth rate of linear function is represented by horizontal line. The example include comparing a number to each and every element of size n requires n comparison. For example, maybe when we are taking linear search algorithm. In the linear search algorithm, what happens? We will take n number of values and we will search one value, or maybe to compare one value in that linear number of values, or many number of values, n number of values. Then we have to compare search value with n number of values. Then the next one is n log n function. This type of function is calculated as fn is equal to n into log n. Fn is equal to n into log n. The function that assigns to an input n the value of n times the logarithm base 2 of n. A log linear growth rate is slightly curved. We can see slightly curved, that is for lower values than higher values. Okay, when the lower values are there, then it will be the resource required may be little bit less compared to the previous one. Okay, or the as per the linear, and afterwards again it will go on in the same way. Okay, the example include possible algorithm for sorting n numbers. Sorting least of numbers may be the example for n log n function. Okay, then the quadratic function. The quadratic function is calculated as fn is equal to n raised to 2. So given an input value n, the function f assigns the product of n with itself. The example includes algorithm with nested loops. If you are using two for loops, it may be an example for quadratic function where inner loop implements linear number of instruction and outer loop implements linear number of times. If you are taking two for loops, inner for loop is repeated, outer for loop number of times, and that concept is called as nested loop, and this quadratic function represents nested loop. So that's why fn is equal to n raised to 2. That means the resource required may be more, okay, here, and that will be represented in this way. If the value increases, the resource required may be increases. Since the inner loop is repeated, outer loop number of times. Cubic function. The cubic function is calculated as fn is equal to n raised to 3, which assigns to input value n the product of n with itself 3 times. The example includes matrix multiplication with 3 loops. That means there are 3 loops in the nested loop. Then we will call it as a cubic function. Okay, in the algorithmic analyzation. And that will be represented in this way. The chart will be like this way. For the beginning, it will be resource required is very less, but afterwards it requires more. Then the exponential function. The exponential growth rate is one where extra unit of data requires double amount of resources. Okay, if the extra unit of data, that means if there are data increase, then automatically the resource required will be doubled. That is the concept of exponential function. It is calculated as Fn is equal to b raised to n, where b is a constant called base and n is called exponent, and that will be represented in this way. So the earlier value, the resource required may be very less, but afterwards resource required is more. Next one is asymptotic notations. Asymptotic notation represents the limiting behavior concerned with the increasing in runtime algorithm with the size of input as a limit. Okay, and there are three types of asymptotic notations: big O notation, omega notation, theta notation. Okay, there are three types of asymptotic notation. It represents the limiting behavior concerned with the increasing in runtime algorithm with the size of input as a limit. Okay, so these are the notations which are used to represent limiting behavior. That means when we go on increasing the input, the resource time increases, and we have to find out how much resource time is required as the input increases. And that to find out, there are notations, and those notations we will call it as a asymptotic notations. And there are three type of asymptotic notation. One is big O notation, second one is omega notation, and third one is theta notation. There are three notations. Okay, sometimes there may be question what is asymptotic notation, and give name three of them. Remember, so big O notation, omega notation, theta notation. So first we will take big O notation, what it is. Big O notation is useful to find time or space consumed by your algorithm. That means to find out the time or space complexity. We can use these notations. Okay, the first one is big O notation. Because we all know one thing, that finding a solution to a problem is not enough, but solving that problem in minimum time or space is possible or not. That is important. Okay, everybody can have solution to a problem, but finding the best solution, okay, that means within the less time duration, is the best one. Maybe one person develops the program, and maybe he will take 1 month to develop that program, but another person, he develops within the 15 days, even with less number of resources, even with less number of memory space, then that is a better one. Okay, these are the concepts, okay, that we have to find out, and for that purpose we will use this notation. If we talk about competitive programming, then you want your algorithm to be faster than others, otherwise you won't be able to perform better than others. On the other hand, when you are working on real life projects or as a software developer, then you want that loading time of your application or other tasks should be executed fast, even in terms of space complexity. In other words, you can say you are on the right track of learning data structure and algorithm, or your development skills when you start look upon the complexity of your algorithm. Okay, so the data structure, that is another concept to go for the memory implementations. Okay, using the memory is important resources, and the data structure is one concept that we will see in the next cell. There is a separate subject called data structure, and algorithms or your development skills when you start look upon the complexity of your algorithm. But from all this we got to know what is the complexity and why we are studying it. Big O establishes a worst runtime. As I said in the last class, there will be three type of cases, scenarios. worst case, best case, and average case. And big O establishes a worst runtime. What that worst runtime means, okay, that we will see. Let Fn and Gn be positive integers. Fn and Gn is be positive integer. That means two values here, Fn and Gn. This notation is represented as Fn is equal to OGN. Okay, so order of Gn. Gn represents set of numbers. Fn, to complete one function, we are taking O of Gn, that is order of Gn. If and only if there exists two positive constants C and N0. If and only if there exists two positive constants C and N0 such that Fn is equal to C into Gn. Fn is equal to C. C is a constant and Gn is set of numbers. Okay. That is, Fn is asymptotically less than or equal to Gn for all values of n greater than or equal to n0. Fn is asymptotically less than or equal to Gn for all values of n greater than or equal to n0, where big O represents upper bound. Okay, maybe for example, just I'll give simple example. Maybe you are comparing values, and when we are comparing values, we'll start comparing from the first number. We'll start comparing from the first number. What is the worst case? Worst case is the given number, what we are searching. It may be at the last position. That is worst case when we are searching. If it is at the first position, okay, good. That is a best case. If it is at the middle position, that may be average case. But if it is at the end, then there may be worst case. Okay. Sometime the searching value may be at the last position. Okay. Then it will take more time to search the value because we are comparing the given value with all the values available in list. And that only big O notation represents. Big O notation represents upper bound, and what may be the worst case value at the end, we will consider it as a worst runtime. And big O establishes a worst case runtime. For example, maybe as a teacher, I want to find out records of one student named Janice. To find a record, so you use a simple search algorithm to go through her school database. And simple search takes O(n) times to run. That means if there are 10 values, it will take 10 times O(n) times to run. This means that in the worst case, you will have to search through every single record to find Janice's. If her record is at the top, then the search operation takes only O1. Only one operation is required. Okay, that may be a best case. In the linear search, if there are 10 records in the database, the worst case may be O of 10. There may be 10 search operations. But in binary search technique, it may be only O of 3. Okay, there are different search operations: linear search or sequential search and binary search. And the sequential search or linear search compares the given value or the search value with all the values one by one to find out the value at the position where it is. But binary search searches in the sorted order to compare the values, and directly it compares with the middle value in the list. And if the value, search value, is in the upper part, search value is less than the middle value, the meaning it may be at the upper part. If it is greater than the middle value, it may be at the second part. Then it will take only the second part, it will leave the first part. Then this type of technique saves time. So that's why he's saying binary search technique may be of only O of 3. And in the data structure, we will study about the binary search technique. And this type of method, okay, saves the resource. So binary search may be only O of 3. For different search algorithm, big O notation is represented as follows. O log n for binary search. And you know, logarithm of n value is very less. You can find out by using calculator. Just take log of 10. So what may be the value? Binary search O log n. On is simple search. If there are 10 number of values in the list, then it will take 10 operations to complete the operation. That is a worst case. So here we have specified worst case. O n into log n for quick sort. N into log n for the quick sort. O n square for the selection sort. N into n number of operations. So O n square. And O n factorial for the traveling salesman problem. Traveling salesman problem is maybe one person is moving from one place to another place, and if there are many number of places in between, then which is the better way he has to find out, and that is called as traveling salesman problem. Okay, and that we will take it by O(n) factorial. Thank you, students. In the next class we will see the examples. Thank you. God bless you.